Have you ever stopped to think about this? Why does gravity, the force that supposedly only pulls on things with mass, why does it also bend a beam of light, which, is massless? It's an incredible question, and it's one that stumped even the greatest scientific minds for literally centuries. And the answer? Well, it completely rewrote our understanding of the entire universe. So let's get into it.
Okay, so here's the puzzle, right? Everything we learn in school says gravity is a pull between objects with mass. But light, which is made of these massless little particles called photons, still gets bent when it passes by something massive. So how in the world does that work? How can gravity possibly get a grip on it? To solve this, we can't just tweak an old idea. We actually have to completely demolish it and start over. And our journey starts with the absolute giant of physics himself, Sir Isaac Newton. You gotta understand, for hundreds of years, his ideas weren't just theories. For all intents and purposes, they were our universe.
Newton's concept was just beautiful, and honestly, it works almost perfectly for everyday life. Every object with mass pulls on every other object with mass. The sun pulls the earth pulls the moon, you get it. The bigger something is, the harder it pulls. Seems pretty straightforward, right?
He even figured out exactly how distance plays into this, with what's called the inverse square law. So, if you double the distance between two objects, the gravitational force drops to just 1/4 of what it was. If you triple the distance, it plummets all the way down to 1/9. This just elegantly explained why planets move the way they do. But it also left this huge, gaping hole in the logic. And here's that problem. How does this force actually work? I mean, really think about it. If I kick a ball, my foot makes contact with it. But the sun and the earth? They're separated by 150 million kilometers of pure empty space. So how does the sun's pull reach across that enormous void instantly? Newton, genius that he was, had no clue. He just called it action at a distance, which is a very, very fancy way of saying, I don't know, it just does. And that mystery would drive physicists crazy for over 200 years. And then along comes this humble patent clerk from Germany with a completely new way of seeing, well, everything. His name, of course, was Albert Einstein, and he was about to turn physics completely on its head. This one statement just changes the entire game. Einstein basically said, hey everyone, that whole picture of gravity as a pull, it's wrong. What we feel isn't a force in the way we usually think about it. It's something much, much stranger. So he argued that the universe isn't just some empty stage where things happen. Nope, it's an active participant. He asked us to imagine it as a single, flexible fabric, a combination of all 3 dimensions of space and the 4th dimension, time, all woven together into something he called spacetime. Now, in this new vision, a massive object like our sun doesn't send out some kind of invisible tractor beam to pull things in. Instead, its immense mass creates a deep depression, a curve, in the very fabric of spacetime itself. The classic analogy is a heavy bowling ball sinking into a trampoline. And this is the other half of the magic. Smaller objects, like our planet, aren't actually being pulled by the sun at all. They're simply rolling along the curved path that the sun has created in spacetime. So what we perceive as the force of gravity, that's just objects following these cosmic contours. So how on earth did he come up with such a reality-bending idea? It wasn't from some lab experiment. It all started with a series of incredibly clever thought experiments, one of which he later called the happiest thought of my life. Okay, first, imagine you're in an elevator and the cable snaps. Yikes, I know. But during that freefall, you'd feel completely weightless, right? Just like an astronaut floating around in deep space. From inside that falling box, Einstein realized the 2 situations are physically identical. There's literally no experiment you could do to tell the difference. Now, let's flip it. Imagine you're in a rocket ship out in deep space, far away from any planet. If that rocket fires its engines and accelerates upwards, you're going to feel a force pinning you to the floor. And get this, if that acceleration is exactly the right amount, it would feel precisely the same as just standing still on the surface of Earth. So here it is, the crucial insight. The effects of gravity are completely indistinguishable from the effects of acceleration. To Einstein, if 2 things look, feel, and act the same in every single way you can test, they aren't just equivalent. They are the same thing. Gravity isn't like acceleration. Gravity is acceleration. And this powerful realization, This idea that gravity and acceleration are really just two sides of the same coin was the final key that unlocked our whole mystery about light. Let's go back to that accelerating rocket for a second. If you throw a ball across the cabin, it's not going to travel in a straight line, right? Of course not. It's going to look like it's curving downwards as the floor of the rocket rushes up to meet it. Now, and this is the incredible leap, what if you shine a beam of light across that same rocket? Well, for the exact same reason, it has to follow a curved path too. And since acceleration is gravity, the conclusion is absolutely inescapable. Gravity must bend light. I mean, this was a prediction so wild, it was basically science fiction at the time. But a theory is just a theory until you can prove it. And to do that, scientists needed a gravitational source massive enough to actually bend light by a measurable amount. And luckily, we have a perfect candidate right in our solar system, the sun. So in 1915, Einstein publishes his general theory of relativity, which includes this totally insane prediction. 4 years later, an astronomer named Arthur Eddington led expeditions to test it. Now, the only way to see stars close to the sun is during a total solar eclipse, when the moon perfectly blocks its blinding light. So his teams took pictures of the stars during the eclipse, and the results were historic. The stars weren't where they were supposed to be. Their positions had shifted, just like Einstein's math said they would. The amount of bending was, well, it was tiny. Just 1.75 arcseconds. To put that in perspective, an arcsecond is 1/3600th of a single degree. I mean, it's unbelievably small. And yet, it was measurable. And it matched Einstein's calculations perfectly. This was the first hard proof that gravity wasn't a force at all, but a fundamental curvature of space-time itself. And that finally brings us back to our answer. Gravity doesn't pull on light because light has no mass for it to pull on. Light is simply doing what it always does, traveling in the straightest possible line through the universe. The trick, the beautiful mind-bending trick, is that the universe itself isn't straight. Space-time is curved, and a straight line through curved space is a curve. So, Einstein proved that space isn't just a fixed backdrop, it's this dynamic, bendable fabric. And that solved the mystery of how gravity affects massless light. But remember the full name of that fabric: space-time. If gravity can bend space, what do you think that means it can do to time?